extreme. You said you want me to do you a favor? To amaze you is the favor?
Yeah, like give me, tell me something which we all believe is true, but it's not true in science.
I don't have I don't have that to offer you.
Wait, you know science, all right? So you know a lot of things which we attend to believe, but the truth that it's not. Like for example, if we believe that x is equal to 2, x equal 2, but in reality, when you study physics, you know that x is not equal to. You know what?
Yeah, but
So
that doesn't happen.
it too.
No.
One example, one example,
What do you mean when one example? What?
want an example. Do you
You
want an example?
you want to give me an
I do.
example? You want
Yeah,
me to give you an example that there is no
yeah.
exception, that everything we know is
It's
physics.
true. No, I'm talking about like let's say a fact which we attend to believe in physics, but in reality, it's not true.
But reality is physics. I mean, what do you think is
Oh,
physics?
uh,
Hmm?
physics is a third dimensional study. We study things which is third dimensional, which is called physical.
Physics is reality. I mean, what do you? Physics is not different than just reality. Physics is exactly reality. Physics is empirical. It's a science. It's just a conclusion of our experience. That's all it is. There's nothing.
Uh,
Mm-hmm. What?
Not really empirical. Empirical is different from empirical doesn't mean physics, all right?
I mean, physics.
Like word, sure.
Physics is a science. Science is empirical. The
Yeah.
scientific method is the empirical method. We don't
Um,
care. Hmm.
Let me amaze you with that, right? So basically, science, I believe, physics is a branch of science, obviously, all right? But science doesn't mean an empirical, or science contains some things which are more than empirical, all right? For example, we have an objective in science, but empirical is different. You can be delusional, like, for example, you can have something in your eyes which make you see different, like you have a red eye, you have a disease on your eyes which make you see blue as a red.
Hmm.
So it would be an empirical evidence that it's red, but in reality it's a blue, right? So
Okay.
empirical evidence is not like the best type of evidence which you can observe.
It's the only evidence we have. So it's the only one. So it's the best one because it's the only one. What is
We
the
have difference.
Mhm.
Sure, you
what
can talk. Yeah,
what's the alternative to empirical?
great question, right?
Mm-mm.
So we have types of reasons. We know that we can deduct reason. Like, for example, you kept coughing, so I deduct that you're sick. Decent.
I don't understand. But the
All right.
you
So let me give
you
you another example.
you observe. No, I mean let's go with one example. So
True.
you see me coughing. You observe me coughing. That's an empirical
No,
input. No,
yeah, but I have deducted. You know what deduction means?
sure.
Or an induction?
I
Right,
mean,
decent.
deduction. I mean, I I don't. Okay,
I
whatever.
can tell you.
No, no, it's okay. But
Like,
what's your point? What are you trying to say?
I'm trying to say that empirical evidence is not the only evidence which is as an actual evidence, right? You can have a scientific evidence, you can have a deductional evidence, you can
Wait
have an
one second.
inductive evidence, you can have an abductive evidence.
Wait,
All
wait,
right,
wait, wait, wait. Hold on. Slow down, slow down.
sure,
So
yeah.
every time I have a discussion with anyone and they say they have an alternative.
Interference?
What?
No. It's an induction. I have inducted from my personal experience, from my personal perspective, that you're sick by seeing you coughing. It's not an interaction. It's not an interference. All right,
Wait.
it's an induction. I'm talking to another one. I'm talking
No,
to another body. I'm not talking to you, right?
yeah, no, talk to me. So concentrate only on me. Forget about Sina.
Wait,
Sina,
wait.
don't interfere. One person. Only we're debating one person. So
Yeah, yeah.
Andrew,
So
it's
no
just me
engaging.
and you. Yeah, don't engage. Sina, stop. Sina, stop. Okay, Andrew, talk to me. So every time somebody comes to me and tells me, I have a new method of knowing that is not empirical, it's not scientific, I tell them, yeah, okay, what is it? And they come up with something, ridiculous.
But
Something. What is
yeah,
your
we
what
science
is
or
what is your alternative to observation, to empirics? What's your alternative?
all right. My alternative would be something which is called a logical reasoning.
Logic.
Logical
Okay, give me
reasoning.
an example. Fine. Give me an example.
Sure, sure. All right. So when you say, I'm gonna give you a wide example, right?
Sure.
For the sake of the debate
Sure.
being continuing.
Sure.
Sure. So in your life, you have seen four black men, all right? You all the men you have seen in your life were white, except four black men, and the
Well,
four
purple,
were
purple, purple, purple.
purple. Yeah, yeah, purple because of the racism. All right,
Yes,
purple.
yes. Hmm.
Yeah, exactly. All right. So you have seen four purple men, and the four were a criminal. So you have made an abduction. Abduction is basically when you made the best assumption from an incomplete. All right. So you have assumed that all purple men are criminal
Okay,
for
but that's
seeing
not okay.
all
But that's
purple men in your
that's
life
okay. Hold on, hold
being
on. 1 second. Okay, look. So you,
true.
so your new way of knowing is what? I mean, you still experienced four purple men who are all criminals. Okay, so
Yeah.
that's still scientific. That's still empirical. How is this not empirical?
It's based on empirical, but it's not an only empirical. So
How is it not
wait, if you
empirical?
say it, all right, I will give an example. Yeah, wait, no
Another
example.
example?
No, 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 no example. All right, I would just answer you straightforward.
Mm-hmm.
Deal. All right.
Sure.
So my empirical basis
Mm-hmm.
where that I have observed it for purple men, and then my conclusion where that they are a criminal or
So how?
all purple men
But
are
this is
criminal.
just a scientific theory, and you're making a prediction based on your scientific theory, and now you can go test. This is pure bacon. This is baconism. This is the bacon
Making
gold standard of scientific algorithm. There's nothing new about your method. Your methodology is absolute standard science.
all right.
Yeah,
Mm, maybe, yeah, you're true.
yeah,
You're true.
yeah,
Yeah, I
yeah,
agree with you.
yeah. So, do you want to do physics? Do you want to talk
I
about
can't
physics?
debate. I cannot debate physics, but I can listen to you talking about physics.
You can debate
Surely,
physics. You can debate.
no, I'm an ignorant. No, I would be looking so delusional
No,
talking about physics. Sorry,
no, no.
not
Here,
my
let
topic.
no, because I don't know physics. I don't know. I don't think anybody
No, no,
knows. I don't think anybody knows physics.
no cab,
I certainly don't
cabbing,
know
cabbing.
physics.
You're cabbing. You're cabbing.
I'm
No,
camping. What?
yeah. Yeah, your performances in physics is way beyond your performance in debating.
Oh, I don't know if that's a compliment or an insult.
It's yeah, it's
It's both.
yeah.
Oh my god.
All right.
Okay, so intro to physics. I don't even know how to spell physics. Okay, so what do we know in physics? What do we know in physics?
We know everything, I believe.
Well, yeah, but
Everything.
okay, so let's start with I would start with F equals
150.
okay, the topic is F equals MA. This is the topic. So you don't know what this means. Or do you? Do you know what this means? Do you can you see? Do you want to guess? Are you there? Or are you disconnecting again? Yeah, he's disconnecting.
No, no, I'm not. I'm not disconnecting. I'm listening to you.
So, do you know
So
what?
wait, where are you? I can't see you. I can't see you.
So just
I cannot see you.
look at the stream. If you look at the stream, you'll see it.
But the stream is super delayed. There
Okay.
is a
So
relation
so
between
go
you and the stream.
so go to Intro to Physics whiteboard. Whatever.
Yeah, I can't see you then.
So just scroll out. You have to scroll away, scroll away, scroll away. Keep scrolling, keep scrolling, keep
Alright.
scrolling, and then you'll see it.
Who's drawing all these?
Scroll. This
I'm
is
scrolling.
keep
I
scrolling
cannot
away.
see
You're
you.
scrolling in the wrong direction. Scroll away.
I
Keep.
can't. I'm at the end of the
No,
map. I
you're
cannot
not.
see anything.
You need to see the piece of paper. Look at the stream. Look at the stream. Here. Look at the
Alright,
stream.
yeah.
The stream is. You see the stream? One
No,
second. Hold on. 1 second. You'll see it. You'll see it. It's
I
coming up.
do.
There it
I
is.
see
You
it.
see? You see, this is the paper that I have written
F
on it.
equal MA. F equal
Exactly.
MA.
Okay, now go to this paper. Go look at the paper so you don't get a delay and cry that there's a delay.
Alright.
Okay, so today we're
Yeah.
going to talk about what is F equals.
Yeah, I knew. Yeah.
Okay, so do you have any
Yo.
idea what F equals MA? Do you know what this means?
Well, I can see it. Wait. I'm going to you.
I
I'm
see, I
going. I'm
see, I
going.
see your cursor. I see your cursor moving slowly.
Yeah.
Okay, do you know what it means, F equals MA? Have you ever heard of this?
Of course I do.
Wait, you know what this means?
Yeah.
Okay, explain it to me.
Sure. F equal ma states that force equal mass times acceleration.
Oh, very good. So,
Uh,
do you believe it's true?
of course I do believe it's true.
Can you prove it from any principle? What would be the principles and
Uh,
how would you derive it from any other principle? I think
wait.
most people that believe it's
Yeah, I know. Sorry, I have a principle which provide an actual evidence to support the theory,
true.
which would be Newton second law of motion.
But what? How would you derive from what would you derive this principle? This equation?
The prin
Hmm.
Yeah, I would prove the validity of the equation by
How?
using Newton's second law of motion.
What do
Can
you
I
mean?
can define it? Sure, I would tell you.
Hmm.
Second, right? So Newton's second law of motion basically states or
Hmm.
define
Hmm.
force as a rate of change of momentum, which would be translated or the equivalent of state of m of F equal ma states that force equal mass times acceleration. So it'd be basically the equivalent or the inductions.
All right. Can you derive this from any principle?
I just say, wait, Newton second law of motion
Let's
is
see,
a
but
principle.
we cannot appeal to authority, so let's not say Newton any
It's,
longer. Just tell me what
it's
principle you're deriving this from.
second law of motion.
Okay, write it. What is it? I'll write it. So, what is the second law of motion?
All right, second law of motion basically states that force
Hmm.
as the rate of change of momentum.
So, it's the rate of change. Let's say delta. Well, what is momentum? MV?
I wrote it. Yeah, I wrote it in the side chat if you wanna see it. I've been writing for eternity.
I don't see it. Oh,
Yeah.
no. But let's draw it. So, it's delta MV over delta T, right?
Wait to see you. Mm-hmm. Mm-hmm. You can keep writing.
I did. I finished.
Wait. Yeah.
All right. So, MV is the momentum. We can say
Mm-hmm.
P is the momentum as defined as M times V.
Yeah.
Okay, but why? Okay, so but why is this true?
Wait. Um. What is the sign for?
What?
Is it equal or congruent?
Oh, defined as. This is definition. Three equal
No,
sign is defined
I'm talking
as.
about the three straight lines.
Defined.
Fine, all right. It means in mathematics congruent, which is a type of triangles.
Oh, okay. Is defined
Yeah,
as.
E equal E, of course.
Okay, so this is just momentum. Momentum is mv. So the change in momentum over time is the force. Okay, why would you say that?
Mm. Can you repeat the question? Maybe I'm not
Just
tracking.
no, just prove this. Prove that F equal. I wrote what you said. That
Mm.
the force
But it's a
is.
principle. I'm not obligated to prove a principle.
What do you
Principle is
mean?
already a factuality, and
What do you mean?
factuality is not proven.
No, we want to prove things so we are
Which already
convinced.
accepted,
No, I don't care what. I don't know what it means accepted.
accepted, right? So the scholars of
I
science,
don't care. Don't appeal. No, no appeal to authority. I don't care about scholars of science. I don't care about anyone. There's only me and you in this
all right,
universe. Is this true? Is force equal to change in momentum over time?
of course.
But yes.
Yeah. Wait. First, before me answering, what's your personal belief, and why do you believe in your personal belief?
What do you mean? I don't understand. What do you mean personal belief?
I'm saying, what's your view?
About what?
Do you agree? Do you disagree?
No, I'm following you. I don't know. I was about to say I don't think anyone can derive F equals ma. I don't think people usually know how to derive F equals ma. They maybe they knew on the first day of physics, but they forgot. But I cannot. I mean, I don't remember how to derive it. So I'm listening to you. So I don't have a personal stance.
I'm bad. I am bad at physics.
We're all bad at physics. I'm certainly bad at physics, so we're together. Anyway, so can we derive F equals delta mv over delta t? Can you derive it? The force is the change in momentum over time. Can you derive it from something, from another principle? I mean, I would say that delta
Uh-huh.
mv, if we assume m is constant, then we could say that F is equal to delta, I'm sorry, m times delta, m times F equals m times delta v. If we assume m is constant, so m is constant, and we have delta v over delta t. We could assume that. Why would we assume that? I would say that F is equal to, assuming constant m, it's v final minus v initial over delta t. What is this? What are you bringing to the? Are you there? Anyway, so the point is, this might already be a definition that, or even one, we could go one step beyond and say that the force is equal to some mass times v final or minus v initial. We can even call it v initial divided by t final minus t initial. Wait, why are you muting yourself? Are you there? I can't talk, but I can interact in here. What happened? Why can't you talk? Is it that late for you? Everybody wants you to quiet down. Oh really? Oh my god. Oh my god. I'm so sorry about that. Anyway, um, So the question is this true? Is F equal to, I mean, is it force? Is that for? Is this the definition of force? Is this where everything starts? That force is the definition of force? All right, we say in the first law of Newton, here to prove the validity that it's true. Okay, so I think the first law of the first law of motion by Newton is the law of inertia. That something doesn't want to change its velocity unless a force is acted on it. So the definition of force is something that changes inertia, and inertia is mass times velocity. So maybe the definition of force, maybe this is just the definition of force, but why is it over time? There's 5 people watching? Why? Why are there 5 people watching? It's just me. Oh my god. And you're not even talking to me. It's overtime to see the Perozes. It's overtime to see. Oh, to see. It's like it's overtime because, right? If you think about it, um, if it's a short period of time, if we're able, oh, that's good. So so it's overtime because the less time, if an object's momentum changes, and this change is what we observe as force, is essential. ME is essential because it measures how quickly. Yeah. So you're saying time is essential because it measures how quickly an object's momentum changes, and this change is what we observe as force. So if it happens over a shorter, let's say the change in momentum is some change in momentum. Well, the question is, if we want it to be over a shorter time, if we are allowing this to take place over a shorter time, then we expect the force to be greater. But the question is, why not mv squared over delta t cubed? Why? And why would it not be the square root of f? Why not something much more complex? Why is it just f equals delta mv over delta t? Jet Leo, do you want to join us? Anyway, I don't know. So this is, we need to think about it. You need to tell me why is it just why is it just f equals ma? Why not something more complicated? Or is it just a definition? No, I don't know. What does it mean because it's true? How do you know it's true? How do you know? How do you know that this is not true? Maybe square root of f is equal to delta mv squared divided by delta t cubed. How do you know? You don't know. And I have proved it's true. How did you prove it's true? Because the attachment? Force definition. Force is what causes an object to change its motion. Okay. Momentum. Momentum is mass times velocity. Okay. Change in momentum. The change in momentum over time equals the force applied. Force is equal to dp dt. Acceleration is the rate of change of velocity. Okay, dv dt. Combine, if mass is constant, then F equals ma. Where's m? M wasn't introduced. The relationship F equals ma is confirmed by many experiments and observations. I don't care. So you just left? Are you? What's going on? Anyway, what are you doing? What are you doing? What are you doing? Wait, somebody's. Oh, Nick. Think about how Muslim women indoctrinate children. Okay, that's much earlier. In the general chat, I can't see the equations in here for force. Yeah, you have to come into the general voice chat, not the text chat, not the general text chat, the general voice chat. I'm sorry that it's the same name. That's just a convention in the universe of Discord. Anyway, so Andrew says, but delta is basically the time length. It's by definition. Andrew says it can be wrong usement of definition, but it's true. Muslim women, lol. All right, Nick, do you know physics? Can you prove to us why F equals ma? Can you talk, Nick?
Yo, what's up?
Hey, what's up? Can
Can
you
you hear
prove?
me?
Yeah, we can hear you. Can you?
Hello.
Yeah, hello. Can you prove F equals
Let me
ma?
turn up your volume.
All right, you can turn up my volume. You can do anything you want to me. Do you want me to
I
sing
can't
you?
hear Andrew.
Okay.
Oh,
No, that was just me checking the stream. I'm always checking to see that the stream is surviving somehow by some miraculous act of the gods of the streams. All right. So, can you prove F equals ma? Can you derive F
I'm
equals
looking at
ma?
this. So you got the square root of force equals delta times mv squared over delta time. Could you like work that out so I could see that?
No, that's what I'm saying. How do you know this is not true? How do you know? Like, I can agree that force equals, like, intuitively, I can agree that force equals mass times acceleration. Intuitively, I can say, yeah, it makes intuitive sense. But can
Yeah.
you prove it? How do you derive that it's true? What's your evidence? Is it empirical evidence? What's your evidence that it's true?
So like the only way I can do that is like, so say you have like a volume of fluid and
No.
that is like the
Stop!
mass.
Stop! Stop! Nick, you cannot go to such places. All right, let me do Chat GPT. Let me ask one second. I'm gonna ask Chat GPT. Um, can you maybe derive F equals ma question mark? Let's see what Chat GPT says. And the answer is certainly. Let's derive the equation F equals ma, which is Newton's second law of motion. Step one, understand the concepts. So a force is an interaction that causes a change in an object's motion. That's good, because this we can agree is a good definition. The step two, why I'm sharing my screen, but why can't I see? Okay, it's better now. No, you can't. But if you look at the stream and you'll see it. Let me see if they can hear you. No, you can't. But if you look at the stream, well, we'll test later that they can hear you. I don't think they can hear you right now, but it's okay. Uh, it's 6 people watching us deriving F equals ma. So I think F equals ma it's really important for people to understand this. Okay. So mass. What is mass? Mass is a measure of the amount of matter in an object. Okay, it's just a measure. It's a metric. So in science, we like measuring things. I would say force is also a metric. It's something that we measure. That's good. Acceleration. Acceleration is the rate at which the velocity of an object changes with time. Okay, that makes sense. So acceleration is the rate at which a velocity of an object changes with time. This is good. This is really good. All right. So Newton's second law of motion. All right. This was Newton. Understand the concept. Is this? Oh, okay. Right. Now Newton's second law of motion. Let's go. Newton's second law states that the net force acting on an object is equal to the rate of change of its momentum. All right, let's see what he says. Newton's second law states that the net force acting on so there's a net force acting on an object is equal to the rate of change of its momentum. Okay, it's just a definition. So he says whatever net force is acting on an object, it's changing its momentum, whatever that is. So some net force, whatever we call force, if you apply a force, it changes the momentum. Now, intuitively, we know what a momentum is. Like an object, if a car is moving and it hits you, boom, you get bumped. You felt that was momentum. If I throw a ping pong ball at you and it hits you, that's momentum. If a fly flies and hits you, that's momentum. Obviously, these are different objects with different momentum. They could all be moving at the same speed, but because they have different masses, then you feel different when they hit you. So momentum is the velocity, maybe with the mass, with affected by the mass, maybe times the mass, maybe times the mass squared, maybe times the square root of mass. I don't know. It's some combination of the mass and the velocity. All right. Momentum definition. Momentum is defined as the product of an object's mass and is so this is just a definition. So this means these are just definitions. So the force. So if the definition of momentum is p, that's the letter that I guess we use for momentum, and it's equal to mv. That's just a definition. So ChatGPT says that this is a definition. This is just a definition. Why are we not defining it as momentum is equal to m cubed times v to the 10th power? Why is it m times v? I don't know. But that. Mhm.
How the momentum of one object gets converted to the momentum of another
Oh,
object.
we're not there yet. I mean, trust me.
Okay.
Maybe we should watch. You know what we should do? We should watch. First of all, you should join me. Why don't you come and join me in the actual stream? Let me give you the link to my stream. Join me in the stream in StreamYard.
Okay.
Click the thing that ends with the 8, T8 at the end. You see the link with the T8? Click that. Tell me that you clicked it.
Is it in the general chat?
No, it's in the side chat of the general voice chat. If you look at the stream, you'll see it to the right. This is where my
Sure.
mouse is. Oh, we're down to 3
Okay.
people now. That's terrible. Well, that's terrible.
Wait, so I got to continue with. It says continue with YouTube or continue with Facebook.
With YouTube. Continue with YouTube.
Okay.
Continue with the YouTube persona. What is today? Is today Thursday? Was today Thursday? Oh my god, it's the weekend. There you go. Okay, so you're still here. You will go to the backstage. As soon as you're in the backstage, I'll pick you up and I'll bring you into the stage. Prepare for the stage. Almost there. You're almost there. Meanwhile, I'm gonna go look for a YouTube video that maybe explains why F equals MA. So you should enter with Nick. Just say enter with Nick. Just say Nick. It doesn't matter how you enter. Okay, so why, or maybe we should derive F equals MA. Can we derive F equals MA? Newton's second law of derivation. There you go. Device not connected. You don't have a microphone. I don't know what that could be. It says you don't have a microphone. Device is not. I don't know what's going on. How did you manage to do that? Okay, there you go. Yeah. That's good. Okay, leave Discord. You don't have to. Yeah, you don't have to leave Discord, but it doesn't matter.
Okay.
Okay.
There we go.
Okay, There you go. Okay, so you're with me in on the stage. So let's
Okay.
mute myself. I'm just gonna mute myself on Discord. Hopefully that will work. Let me see. Okay, let's go. So let's see. Oh, I'm hearing myself from you.
Oh
Are
shoot.
you using a headset?
Let me turn you down. One
Oh,
second.
you don't have a headset?
Yeah, I got a headset. It's just the microphones are real loud on it. So uh or I mean the speakers. So I need to turn your volume down.
Okay. I can hear myself. I can just barely hear myself. It's not the end of the world. I'm not gonna die. Okay, so let's try to go listen.
Can
Let's
you
go.
hear yourself now?
No, it's fine. It's fine. Let's go
Okay.
listen to this guy. Let's see if he's any good.
Okay.
And that then to derive the equation F is equal to ma. So to start this one off, we use Newton's second law, which tells us that force is proportional to the rate of change of momentum.
Interesting. Force is proportional.
So we can write that as
But not over time,
force
That's a good question.
is proportional
So that's the proportional sign. It's not equal, it's proportional.
right? Gotcha.
to change of momentum over time.
Oh, he didn't say change the momentum over time, but he didn't write it, but he's saying it.
Okay.
Oh, he's saying rate. Rate means over time.
Okay. Gotcha.
And that
Gotcha.
then can be written as F
So change in momentum over time.
is proportional to the change in momentum is m times the final velocity minus m times the initial velocity over
Gotcha.
t. Now we can factor out our m here, so F is proportional to m times v minus u over t. Now v minus u over t, well, that's just acceleration. So now we have F is proportional to m times a,
But it's not equal to, okay.
mass times acceleration. If we want to get rid of this proportionality sign and make that an equal sign, we need to bring in
Oh,
a
I see. Okay.
constant
So
of
he's just getting the acceleration, and then he's multiplying the mass times the change in momentum over time. Okay. Which is acceleration. Mass times acceleration.
I don't know. I don't know. I mean, I'm not so happy with this derivation because let's see how he ends this. How he gets rid of the proportionality.
proportionality. So that would be F is equal to K, which is our constant of proportionality, times MA. And K is equal to 1.
K is some constant. And
Gotcha. Gotcha.
that's the definition of proportionality.
I'll explain why that is in a second. If K is equal to 1, that means F is equal to MA, which is what we were asked to show in the first place. Now, why is K 1? Well, the force is 1 Newton. If we define 1 Newton, so F is equal to 1 Newton. In this case, if we have a force of 1 Newton, that means we have a mass of 1 kilogram, and we have an acceleration of 1 meter per second squared.
Someone has. Oh, Lily. Yo, what be happening? How are you? We're doing introduction to physics. We're trying to understand why force is equal to mass times acceleration. Do you know why force is equal to mass times acceleration, Lily? We're not drawing, so we're not there. We're watching a YouTube video. Lily, we're watching a YouTube video.
So meters per second. Okay, so meters is the Newton, right? And then per second squared.
Oh my god. She came in, she scribbled on the whiteboard and she left. It's like every day I come in, I look at the whiteboard, it's always scribbled on with Oh my god! Every day they come in, they scribble on our whiteboard, and they leave. So every day I come in, I look at this. It's always scribbled on. I never know why. So
Mhm.
it's probably just Lily every day coming in scribbling. So funny. Okay. Yeah. Look, I don't know. I honestly I don't understand
Okay,
it.
1 kilogram.
But
Okay.
how does he know this? Okay, let's continue listening. I don't know how he knows this. How do you know this?
And if we sub in 1, 1, and 1 into the equation here, we
Okay,
get
this is
K is
useless.
equal.
Let's try Professor Dave.
Professor Dave again. I want to tell you about Newton's second law. He knows an
I want to kill myself, but you're not helping.
object will continue its state about Newton's first law of motion, which tells us that an object will continue. Professor Dave explains. We learned about Newton's first law of
This guy, I don't like him so much personally, but he's actually a pretty decent scientist.
Hell
Uh,
yeah.
yeah, he's pretty good. I mean, I don't know how much I agree with him on many things, but I like how much he is. When he defends science, he does actually a decent job. Like relative to the fact that he's kind of pompous and like something about him is pompous.
I can't hear you. You're cutting out.
Why am I cutting out? That doesn't make any sense. Something is wrong with your end. That shouldn't be happening. That should not be happening. You should be hearing me very well. There's no reason. How is my audio now?
Oh wait.
Can you hear me? Yeah, you have some background
Oh,
noise.
shoot.
What happened?
There we go.
Okay. What happened?
Oh, I don't know. I had my volume down.
Oh, that's nice.
It's good now.
Okay, so let's listen to Professor. He's not a professor. He has a master's, but let's hear him.
motion, which tells us that an object will continue its state of motion unless acted upon by some net force.
That's pretty good. But I don't think this is Newton's first law. I think this is Galileo. I think Galileo came up with it, and Newton just took it, said, "Okay, let's run with it." We did 6 messages, 6 notifications.
Wait,
I think.
didn't Newton come before Galileo?
No, Newton is like 1600s. Galileo is 1500s.
Oh, okay.
I think that's pretty much the time. I think there's like 100 years between them, or something like that. When was the Black Plague? I think Newton was the Black Plague, so Galileo was pre-Black Plague. Newton was the
Okay.
actual Black Plague. Newton did all his work at home because of the plague.
The
Oh yeah,
second law
Galileo
continues.
studied speed, velocity, gravity.
Yeah, Galileo was pretty advanced. Yeah, Galileo was pretty amazing. I was listening to Galileo physics. It's really advanced. I mean, it's really difficult to follow. It's not straightforward. Anyway, what if there is indeed a net force by? So this is an interesting statement. An object will preserve its state of motion unless acted upon by some external net force. That's pretty amazing. That's pretty amazing because you don't think about this like in day to day. This doesn't happen. Like things don't just preserve their motion unless acted upon. It's like things tend to not move. But then you think about it. Why do they tend to not move? Well, it's because they're acted upon. Like things, like forces tend to stop things. It's usually friction that ends up stopping everything. Okay,
Yeah,
let's
they
go.
were pushed or
Continues
something. Yeah.
There, describing what will happen if some net force is indeed present, whether from internal or external forces. This law tells us that force is equal to mass times acceleration. This is summarized in the following equation.
Okay, so Newton's second law. One second, I didn't get. How did he skip to the second law so quickly?
External forces. This law tells us that force is equal to acted upon by. He knows a lot about. We learned about Newton's first law of motion, which tells us that an object will continue its state of motion unless acted upon by some net force. The second law continues from there, describing what will happen if some net force is indeed present.
I see. So it's a story. So the first law says an object will preserve its state of motion unless acted upon by some external net force.
Mm-hmm.
Okay, now let's talk about what if that net force actually acts upon it. This is unless. This is unless acted upon. So as long as there is no, this is like Einstein's relativity. It's like special relativity is unless it's an accelerating framework.
Right.
In this case, unless acted upon by some external body. What if there is indeed a net force present? Force net. That's the second law.
Whether from internal or external forces.
What's an internal force? 1 second.
The second law continues from there, describing what will happen if some net force is indeed present, whether from internal or external forces. This law tells us that force is equal to mass times acceleration. This is summarized in the following equation, F equals ma. What it means is that we can do quantitative calculations relating the magnitude of a force applied to an object, the mass of the object, and the magnitude of the acceleration
Yeah, but how do you derive it?
that object will experience. And it shows the derivation of the Newton as the SI unit of force when we plug in 1 kilogram and
Okay, 1 kilogram times 1 millisecond.
No, but he's not deriving. He's just telling us about. He's not deriving anything.
1 meter per second squared for mass and acceleration. There are a number of things we can say about this equation, which is tiny but powerful. First, it means that heavier objects will require the application of greater force in order to achieve the same acceleration as lighter objects, with acceleration being equal to force divided by mass. If we want these objects of varying masses each to accelerate.
Wait, go back to that.
Yeah. Wait. He's saying that heavier objects require more force. Okay, so if we increase the mass and we want to maintain the acceleration, we have to increase the force.
Got
If
you.
we maintain the mass and we want to increase the acceleration, we have to increase the force.
Got you.
If we increase the force and we hold mass, we'll increase the acceleration.
Can we play with that with like equations? Like with he said, okay, so if you divide the mass by the force, you get the acceleration, right? Or wait, no, you divide the force by the mass, you get the acceleration. You divide the force by the acceleration, you get the mass.
I mean, I don't know what's given, but the question is, okay, this is a relationship. The question is, how do we know that it's true?
Objects, with acceleration being equal to force divided by mass.
Yeah.
If we want these objects
That comes out, but how do you know F equals ma?
of varying masses of the, this also means that the second law can be rephrased
Okay.
to state that the acceleration an object experiences will be directly proportional to the force applied and inversely proportional to its mass. It is important to note that the net force is the sum of all the forces acting on an object. If multiple forces are acting on an object, which is often the case, we will need to represent them all in a free body diagram and then add up all the vectors to find the net force, which will tell us the direction of the acceleration that will occur in response to the net force. This kind of vector addition allows us to make predictions.
We need to actually read maybe Principia, Newton's book, to understand how he came to this conclusion.
Yeah,
about the motion of an object, even when it is being pushed or pulled.
Let's ask ChatGPT, how did Newton derive F equals ma? How did Newton derive F equals ma? Isaac Newton's derivation of was not presented in the form we commonly use today. Rather, Newton's approach was rooted in his conceptualization of motion and force, which he articulated in his seminal work, the Philosophy Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy. Natural philosophy is what we today call physics, published in 1687. Okay, so Newton's approach. Newton's formulation of what we now recognize as F equals ma can be understood through the following key points. Law of inertia. Newton's first law states that an object will remain at rest or in uniform motion unless acted upon by a net external force. This sets the stage for understanding the relationship between force, mass, and motion. Okay, first law, that's simple. I don't have a problem with that because it doesn't say anything really. It just says a principle. There's no mathematical identity definition, but he did say force. Definition of force. Newton defined force in the context of changing the state of motion of an object, particularly in terms of its momentum. Momentum. This is not something most people think of. That force is a change of momentum. So momentum P is defined as the product of mass and velocity. P equals mv. Why? Why is it not P equals the square root of m times v to the 10th power? Newton's second law in Principia. In the Principia, Newton expressed his second law as the change of momentum being proportional to the applied force and occurring in the direction of the force. So this is how he defined it. So the force is proportional to a change in momentum over time. That's good. He didn't say it's equal to, he said it's proportional. But he did say that it's not proportional to the square root.
It's the extra force of the net force.
What?
So you have a net force, and then you have the extra bit, which is the change in the momentum over time.
No. What are you talking about, Nick?
Yeah, because if you have a bunch of net forces, they'll cancel out.
No, stop, Nick.
delta
Why do you
from the
always
momentum.
confuse? You always confuse me. Because of you, I always fall asleep. You're always killing me. I cannot handle it. It's too much. You're like, everything is even more complicated. Okay, here the PDT represents the rate of change of momentum. But how does he know this? How does he know forces, or is this the definition? Is this definition? Newton expressed his second law as the change of momentum being proportional. How does he know it's proportional and not proportional to the change in the second power or something? How does he know? How do you know this? How do you know this? Here, the PDT represents the rate of change of momentum.
Wait, when you said second power, what did you mean by that?
Well, this is, how do you know it's proportional to the PDT and not to the PDT squared or the square root of the PDT? 1 second, I have a message. Let me read the message. Oh, 1 second. 1 second. Let me just send a message. Okay, so let's wait. Okay, I'll wait for a response. Okay, let's continue. Anywho, constant mass assumption. For cases where the mass of the object is constant, as it often is in classical mechanics, the rate of change of momentum simplifies to F equals m dvdt. Since the vdt is the acceleration, a is a, it simplifies to F equals ma.
Okay.
F equals ma is just a simplified case of F is proportional to the PDT.
Got you.
What do you mean? Got you. F
Well,
equals ma is just all it means is assuming the mass is constant, then the force is equal to the mass times the acceleration.
yeah, it's a
Really,
simplified thing. So you got delta P over delta T, which is A, and then times the mass, which is kilograms,
delta P over delta T is not
equals the
A.
force.
No, delta P over delta T is A only if M is
Oh, my
constant.
bad. You're right. I see what you mean. My bad. Yeah, so delta V over delta T is
One
A.
second.
My bad.
Mm, 1 second.
Mm-hmm. Got it. I see. I fucked up. Delta V over delta T equals A, and that's meters per second squared times the mass, which is kilograms, equals the force. Okay.
Let me just make sure that.
I mean, is that right? Did I explain that right?
Okay. I don't know. What did you say?
Okay, so I said delta V over delta T, that is meters per second squared, and then times the mass,
Delta
that's
V over.
kilograms.
Well, first you need to understand what V is.
Okay.
V is just velocity. Velocity is meters per second. But anyway, let's. So, this is so painful because no one is talking about this bothering. Thus, Newton implicitly derived F equals ma by assuming that the mass remains constant and recognizing that the force applied to an object results in an acceleration proportional to that force. Historical context. Influence of previous work. Let's see what previous work he worked on. Newton's work built upon the earlier ideas of Galileo, who studied acceleration and motion, and Descartes, who contributed to the understanding of momentum and conservation principles. However, it was Newton who unified these concepts under this law of motion, providing a comprehensive framework that could be applied broadly to physical phenomena. The Principia, Newton's Principia, is written in geometrical style, which was common at the time, and much of the modern notation formulation of F equals ma came later as the field of physics developed.
Got it.
Summary. I don't care about the summary. I don't care. This is no good. This is no good. No good at all. What do you mean Descartes and Galileo? What did Galileo think? Let's ask ChatGPT. So what did Galileo? We need to just read the Principia. I don't see any other way around. Can we just read the Principia in English? I need to hear how did he derive it? I mean, why is it?
So
I mean,
ChatGPT can't do like geometric things. It can't spatially organize shit. So
like
that's the problem.
ChatGPT says, well, it's based on Galileo. Really? Can you tell me more about that? That's what I want to know.
Yeah.
Influence and this is what I want to know. So you know what? Let's just take this, drag this to here.
Mm-hmm.
You can't. It says plus. Why can't you drag it? It doesn't let you drag.
Just Control C, Control V.
Yeah, I don't have a choice. I don't like doing Control C, Control V. I feel like it's too controlling of me. Anyway, let's see. Isaac Newton's formulation of his law of motion, particularly the second law, F equals A, was indeed influenced by earlier work, most notably by Galileo, Galilei, and René Descartes. Galileo's contribution. Study of motion and acceleration. Galileo's work on the motion of objects, particularly his studies on inclined planes, led to the understanding that acceleration is constant for objects in free fall. Okay, but that's gravity. It's like,
Yeah.
yeah, he discovered that the distance covered by a falling object is proportional to the square of the time it has been falling. A key insight into the nature of acceleration.
I got it. Got it. Yep, I see it. So the gravitational constant squared, or
No, no gravitational constant.
all right. Well, no, the for Earth, the small g, right?
No, yeah, but so Galileo discovered that the distance covered by a falling object is proportional to the square of the time. This is important. Concept of inertia. Galileo also introduced the idea of inertia. So Galileo figured out that x equals 1/2 at squared.
Uh-huh.
Also, concept of inertia. Galileo also introduced the idea of inertia, which states that an object will remain at rest. So everybody's saying F equals ma. That's you don't know that. Stop saying that. You don't know that. You don't have evidence for that. There's no evidence for that. You need to go. Come on. Why would you say that? Based on
Meters
what?
per second squared. So 9.8 meters per second squared,
No,
regardless of the math.
stop it. I don't care that that's the answer. Anyway, concept of inertia. Galileo also introduced the idea of inertia, which states that an object will remain at rest or in uniform motion unless acted upon by an external force. This idea, so this is Newton's first law is actually Galileo's law of inertia. So Galileo came up with inertia. All right, Descartes' contributions. Okay, Descartes just means from Carthage, doesn't it? Cartes means the cards, because Descartes. This is French. Des just means from, and
Uh-huh.
carte. That's French for many cards. What's a cart?
Is it really?
Yeah, from the carts, like a place called Carts, or there's a place called Cart, and there's a few places called
Map.
Carts.
From
What?
map. I guess hold on. So Cardi is map.
There must be a place called Cart, and Rene Descartes was Rene from Cart, like from one of the carts. I don't know
From
where
map.
is. It's probably the name of his city. That's what they used to call people, like Rene from the city of cards. It's just
Okay.
like Galileo Galilei. I think he was from Galilee or something. Who knows? All right. So Descartes. So conservation of momentum. So Rene Descartes.
Dweller at the outskirts of town.
Yeah. Rene Descartes developed early ideas about momentum. Oh, because Galileo didn't say anything about momentum. So Galileo spoke a lot about gravitation and acceleration. Galileo didn't know anything about momentum. I don't think Galileo did any experimentation with momentum, except for inertia, which is a type of momentum. All right, so Descartes. So it's amazing. So Newton read Galileo's work and he read Descartes' work and he combined them into a new philosophy.
So
All right.
inertia. Hold on. Inertia is just like the inverse of momentum, right? It's like the force acting against the momentum.
No.
Wouldn't it be?
And look, I don't know. I don't know. I honestly, I don't know. I just don't. I don't know these things. I'm trying to figure it out.
Okay.
Anyway, let me take a sip of water before I kill myself.
Okay.
Oh my God, I want to kill myself. All right. Conservation of momentum. Rene Descartes. It's like my entire life I've been wondering, how did Newton figure out F equals ma? Can somebody explain this to me? And I'm trying to think about it, and no one ever explains it.
Right.
And now,
too.
finally, I'm realizing, well, he didn't actually figure it out. He just read it in someone's book.
Yeah.
Now we need to read those books to listen to how they figure it out. All right. So Descartes' contribution. So conservation of momentum. So Rene Descartes developed early ideas about momentum, which he described as the product of the size. So he didn't even know what a mass was. He said size. And speed, he didn't even know what a velocity was of an object. So Descartes also articulated the principle of conservation of momentum in collisions,
Well,
which
hold on.
became
So
Mhm.
velocity is a direction. It's not necessarily the speed. So he was right about speed, but he was wrong about size.
He was right about me killing myself, but he was wrong about me killing myself. But he was right about me killing myself,
For sure.
for sure. Anyway, let me take another sip of water so I can kill myself finally. Let me imagine I'm drinking. Let me imagine I'm drinking poison. Let me just imagine. Let me indulge myself.
So velocity magnitude would be the speed. So the speed in a specific direction.
But what about the velociraptor? What do you think about velociraptor? That's the question.
Oh, that's a claydistic thing, right?
I don't know. All right. Anyway, so let's finish reading this sentence. So Descartes also articulated the principle of conservation of momentum in collisions. This is incredible. So this is good stuff. So did he actually do experiments with collisions, which became fundamental in the development of Newton's laws? Cartesian physics. So Cartesian is anything that has to do of Descartes. Descartes is because he's from Cart, so he's Cartesian.
He's from the outskirts of town.
Exactly. So Descartes' approach to physics involving the analysis of motion and interaction directly influenced Newton's thinking. However, Descartes' laws were more qualitative and less quantitative, and Newton was able to formalize them with mathematical precision. How? How was Newton able to do that? Can somebody please explain it to me? Newton's unification. Let's see how you did the unification. Newton's genius lay in his ability to unify these concepts into comprehensive framework that could be applied universally. Very nice. He took Galileo's concepts of acceleration and Descartes' ideas on momentum and created a coherent set of mathematical laws that could describe a wide range of physical phenomena. His second law, F equals ma, encapsulates the relationship between force, mass, and acceleration, providing a precise and powerful tool for understanding motion. The unification of previous ideas into a clear mathematical framework allows for the application of these principles to everything from the motion of planets to, okay, I don't care. Anyway, we need to know more about both Galileo. So let's say Galileo's. Let's say the study of motion. I don't care about Galileo's inertia. Let's take just this. Let's copy and paste it. Oh my god. Oh my god, please. Okay, so Galileo Galilei's work on motion acceleration was groundbreaking in the development of classical mechanics. My finger is breaking off from having to press the mouse. I'm going to use my my keyboard. All right. So Galileo Galilei's work on motion acceleration was groundbreaking in the development of classical mechanics. His experiments and observations laid the foundation for understanding how objects move under the influence of gravity. Okay. Galileo's experiments and discoveries. Inclined plane experiment. So everything is based on experimentation. They don't tell you this. They don't tell you this. It's based on experiments. It's empirical. Did you know this?
Yeah, like geometric stuff. Yeah.
No, I didn't say geometric. I said empirical.
Observations. Yep.
Wow.
So
said-
like
You said the
So-
right thing. Usually you say the wrong thing. Today, this is the first time I hear you say the right thing.
I'm not
Today's
really so sure I say the wrong thing, but maybe just a different perspective. So like the observation of the geometric properties of
why
how it works in
geometric?
reality,
Why do you say geometric?
because
Why
it's
do you say-
geometric. Like, so the distance and all that, those are geometric relationships, and they're using inclines, and they're using the gravitational acceleration here on Earth to measure that.
Oh my god. Oh my god. All right, let's continue. It's up to you. Look, let's continue. So,
Okay.
inclined plane experiments. Galileo conducted experiments using inclined planes to study the motion of objects. By rolling balls down a slope, he was able to slow down the acceleration due to gravity, allowing for more precise measurements of time and distance. Through these experiments, he discovered that objects accelerate uniformly, meaning their velocity increases at a constant rate over time. A constant acceleration in free fall. One of Galileo's key insights was that in the absence of air resistance, all objects fall with the same constant acceleration, regardless of their mass. This already tells you that gravity should bend light. This already tells you gravity should bend light. This already tells you that gravity
Wait a second.
is
But light
the
doesn't have a
flow.
mass.
Exactly. It says here, regardless of
Oh,
their mass.
okay. Got you.
So if it's regardless of the mass, that means everything falls. That means basically light should fall. That means that gravity is 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 the flow of the ether. That right now there is ether flowing through us, sucking our bodies into the ground. Therefore, we are waves in the ether. Therefore, everything is a wave. Therefore, quantum field
Wait,
theory.
no, it's not a
Yes.
wave.
You're a wave.
There's some things that are waves, and then there's some things that are like continuous flux.
What?
Yeah, there's some things that are waves.
A continuous flux is the ether. That's gravity. Gravity is a continuous flux.
So wait a second. So if say you have a fluid, right? It can be
Yeah.
moving or it can be vibrating. So those are two different things.
Yes. So the motion of the fluid, that's gravity, and the vibration of the fluid, that's me and you.
Yeah.
We are vibrations in the ether, and so is everything we experience. Every atom, every subatomic, every elementary particle is a wave in the quantum field, which is the ether. And the dragging, the actual flux, the actual motion of this field, that's gravity. And gravity bends light because the motion of the fluid drags everything, all the waves in it, including light.
I'm not sure that's how it works.
What's your
I think
Then how do you explain? Okay, then how do you explain that the apple falls from the tree to the ground?
it has more to do with Planck's constant not being a constant, but rather being a local constant. So if you have different g values, that means you have.
How do you explain? How do you explain the apple falling from the tree towards the ground? How do you explain that?
Yeah, so if you have different g values, you have a g differential between them once you subtract.
How do
get
you
the difference.
explain apple falling to the ground.
Can I show you on can I get in
No,
the
I don't
channel?
want to see. I don't want to see. I don't want to see you doing that.
Okay.
That would be
So I was gonna
embarrassing.
explain it. You wanted me to explain it, so
Well, can you do it with without showing us?
yeah. Okay. So
Because we are not, we are G rated, so we don't do
Uh-huh.
those things.
okay. So let's take like an extreme example, like a black hole.
We don't do it. No, we don't do extreme stuff on this channel. We're very like low key.
So everything is derived from this Planck value.
Oh my
Wait.
God! Can I kill
Hold on.
myself now,
Hold
or
on.
do I need
Hold
to
on.
do it
Hold
later?
on. Hold on. So the speed of light is equal to the
What
Planck
about the
divided
speed
by
of?
the-
What about the speed of the speed? What do you think about that?
Yeah. Okay. Well, we can do the speed of the speed too. So
Oh, but
that
what
is the
about?
Planck time.
What about? Everybody talks about the speed of light, but what about the slowness of light? Can you talk about that?
Yeah. So if you have a different Planck value,
Oh my
divided-
God! But what about the angle of the Planck? What do you think about that? Bet you didn't think about that.
yeah, I thought about that too.
Oh
So
my
the
God.
curvature in their alignments. is
Oh
due to the
my
differential
God!
size.
The curvature, differential. Oh my God! How do you do that? How are you such a genius? I need
I'm
to
not a
understand.
genius. I'm an idiot.
Oh, you are a grand genius. The
I
grandest.
wish. I wish. I would understand the whole thing if I was a genius.
Look, to be a genius, you just have to not be understood by anyone. So just say gibberish.
Blah,
Like me.
blah, 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 blah.
Yeah, exactly. And now everybody thinks you're a genius.
Newton was probably a genius. Galileo was a genius. But I'm not no genius.
But I'm not Galileo. I'm no
Definitely not.
Galileo. Anyway, let's read more
You
of
might
this.
be. I'm not.
Oh, I'm definitely not. Oh my God. You know, when I last flew out of the United States of America, so my Uber was like this Latina chica, mucho bonita. I was like, when I'm flying away, but when I come back, we got to get together. She's like, okay, take my number.
Well,
So I
hell
took
yeah.
her number. Yeah, but this is, it's going to be such a long time until I come back. Oh my God. Oh my God. Oh
You
my
forgot
God.
to call her, didn't you?
I'm not back. I'm still away. I'm away for, I don't even know for how long I'm going to be away. Okay, let's continue reading this nonsense. All right, so this was contrary to the Aristotelian belief that heavier objects fall. So he believed, what did he believe? So one of Galileo's key insights was that in the absence of air resistance, all objects fall with the same constant acceleration regardless of their regardless of their mass. So this is incredible because everyone until that time, they believed that heavier objects fall faster. This was contrary to the Aristotelian belief that heavier objects fall faster than lighter ones. Galileo showed that the acceleration due to gravity is the same for all objects. So he showed it, leading to the conclusion that the distance fallen is proportional to the square of the time of fall. Mathematical formulation. Galileo expressed this relationship mathematically, showing that the distance d an object falls. Wait, an object. What's going on? Oh, every time I get to d, it loses. Okay, an object falls is given by d is proportional to the square of time,
Okay.
where t is the time elapsed. This quadratic, it's called a quadratic relationship between distance and time, was a significant step toward understanding acceleration as a fundamental aspect of motion. All right, so this is so incredibly enough. So Galileo derived the notion of acceleration from gravity, from experiments with gravity. Key insight into acceleration. Galileo's discovery that the distance covered. Wait, how many people are watching this? This is a good stream. Oh, there's 3 people watching it. That's very, very good. Do you know who said this? Very good. You know. Anyway, it was the emperor. So Galileo's discovery that the distance covered by a falling object is proportional to the square of the time it has been falling was crucial. It provided the first clear understanding of acceleration as a measurable quantity. This insight paved the way for Newton's later work, where he defined acceleration as the rate of change of velocity and ultimately formulated the second law of motion, F equals ma. Galileo's work demonstrated that the behavior of objects under the influence of gravity could be described mathematically, leading to the deeper understanding of the natural world and setting the stage for everybody killing themselves. Did you know that?
Hey, I got a question.
Sure.
Okay, so say you have two different like powers going the other way, so and they counteract each other. The difference between those powers would be a force, right?
I have no idea. Why are you saying power? Power is like a different thing.
So you
Power
have
is
the okay.
Power, I think, is the ability to do work over time. I think it's something like dw dt. It's how much work can you do in an amount of time? Like
Okay.
the amount of work you can do, that's energy. That's like how big is your gas tank? That's how much work you can do. So let's say
Got you.
work day, you have a full gas tank. Well, that's the amount of work you can do.
So let's
But
say you have
how
two cars, right?
No, but how much power exactly? But how much power can you generate for one tiny job? So let's say we need to pick up a big rock. Do you have enough power to pick up that rock?
Oh,
So
I see. It's relative.
if the rock weighs 1 kilo, yeah, you can pick up a rock easily. You can pick up a rock and another rock and another rock and another rock, and over the day, let's say you can pick up 1,000 rocks. Okay, but can you pick up one rock that weighs 1,000 kilos, like 1 ton?
Right.
So maybe
So
you
power
cannot.
is relative, right?
So you cannot. You don't have enough power. Your engine doesn't generate enough power. It cannot do that much work in such a short time. It can
I
do
see.
that much work over a day, but not over like 1 second,
Right.
1 minute.
I see what you mean.
That's power. Power. Okay. So we need to learn more about Galileo and what he did and how he did it. So let's go back to this tab. Let's go back to, we don't actually care about F equals ma. F equals ma, that's like 100 years later. So the first step is
Wait. Okay, so I gotta figure this out. I gotta get this right. So, how am I gonna do this? Okay, so if you take a power, right? You can if you have a power moving a oh man, this is so hard. Um,
do you mind if I kill myself while you're thinking?
yeah, go ahead.
Oh, thank you. That's very important for me.
Go ahead, do what you were doing, because I'm
okay.
like confused.
Oh, you're confused? Well, don't be, because I'm gonna kill myself. Anyway, so let's go and see Galileo's experiment. Let's talk about Galileo's. Oh, it's over there. Okay, Galileo's experiment. Let's talk about Galileo's experiment. Oh, look, it's Mr. Halili, Professor Halili. I love him. Let's go listen to him.
when you
Is it going to break the ceramic? Worried.
drop it from higher up,
Awesome.
That is awesome.
this time the ball easily breaks the tile, which means it must have accelerated.
Oh my God, that's proof. That's genius. I love these proofs. It's like, how do you know it accelerated? Genius. Unbelievable. This
Okay.
the very first time humans actually measured gravity itself. Jesus Christ. You
Yeah,
realize
that's awesome.
there used to be a window here. You see this? I think
Yeah.
there used to be a window here. And this is actual support. This is an arch. It supports.
Oh,
This is actual support. So otherwise, this window is going to carry all this weight on top of it. With
right.
this arch, so you're spreading the load, and basically there's no load on this window. It's not going to break.
Got it. That's
I'm
a cool observation.
I hope. You see, there's an arch here too.
Yeah.
It's an arch. Amazing, unbelievable. But okay, let's listen.
He built a long wooden ramp, rather like this.
That is long. Jesus Christ! Look at that and that's a big table. That's a big room. Where'd you get such a big room? I think in the old days they just used to have big rooms. And look at the height of the ceiling.
So they're trying to exaggerate the acceleration.
Right, he needs a lot of time to measure. So he was lucky that in those days they had big chambers, big rooms.
Mm-hmm.
But I don't think they had carpets. I think there is carpet. I don't think they had carpets in those days. But you see, it's like there is bricks on the outside and bricks on the inside.
Yeah.
Interesting. And there is a fireplace. What's over the fireplace? Oh,
I think it's
what
a picture.
yeah, I think it's just a picture. So it's like, isn't that a little dangerous to put a picture over the fireplace?
That's a good point.
Wait, and is this where they store the wood? Are these? What is this? What are all these? Anyway,
What is that?
I don't know. Let's continue. Okay, so let's look at this. This is an unbelievable plank, and he made sure it's perfectly straight, but at a constant angle. Unbelievable. And he put the pillows here, so every time the ball finished dropping, it will fall. I would put like a bowl here, so I don't have to run around and get the ball every time. But maybe, where did he get the balls from? You need to make perfect balls. How do you do that?
That he had sloping at a shallow angle.
Oh, it's a shallow angle, so it speeds up very, very slowly. Wow.
The idea was to
But they didn't have clocks. How could they measure time?
roll balls down the roll to reduce the effect.
So as far as I know, for a clock, he used his own heartbeat. Did you know
Oh,
that?
he did? Did he
That's
really?
what they didn't have a clock. What did he do?
Wow. That's pretty awesome.
And this is before the invention of the pendulum clock. So they didn't have clocks. They only had like sun clocks. So that's not very useful.
Right, that's not very
of
that's
wind
slow.
resistance. It also meant that the
Wait,
ball
what about-
angle looping at a shallow angle. The idea was to roll balls down the ramp.
So they don't teach you this. When they teach you F equals MA, they don't teach you all of this. F equals MA. Trust me, bro. F equals MA. What, you don't believe me? Why don't you believe me? Why don't you believe me? Oh my God. This is so delicious and nutritious.
Galileo's
Wait,
experiment.
let me take a sip of water so I can kill myself. 1 second. I love the taste of water with poison. Oh.
I say we because I have a couple of
Oh, man buns. How could we
Man
do
buns.
without man buns. It's not really a bun. It's like
He looks like a ninja or something.
yeah. I think this guy is Asian too, but he has major acne. All right, we'll forgive him. And there is a chick over there. Who is she? And why is she dressed? Oh, it's winter. Okay.
Willing volunteers, Gavin and Joanna.
Joanna. So she's like from the Netherlands or something. Where's Gavin from? He's British.
3, 2, 1, go.
Wow, she's hot.
He's hot as fuck.
Unbelievable. Jesus. Wow. Good job, Joanna. Wow, she's like a scientist. Unbelievable. I would learn every science she could teach. I would sit in all her classes always.
Hell yeah.
Joanna 1, everybody else 0.
A quarter of the way down the ramp, go.
Good job, Joanna. Perfect nose.
Stop. Okay.
You know what I would do? I would pee in front of her because that's more scientific.
I would too.
Because we need to be more scientific, in my opinion, you know?
Yep.
So now half of the way down, go. Stop.
Wait, look at her thighs. Good thighs.
Half of the way down, go.
Perfect thighs. Jesus. She does good. She does squats. I guarantee it. She must spend a good time in the gym every day. Very good, very good. Anyway, so okay. So now they're dropping it from Joanna's dropping it from half the distance, and he's peeing in a cup, so he needs to pee. Wait, so how much do you think he's gonna pee compared to the first experiment? So it should
I
be.
see. He's using the rate of flow to measure the rate of acceleration of the ball.
And he's assuming that the rate that the water flows into the cup is constant, which it's not.
Right, that's not.
It's actually
The water pressure decreases.
Exactly. Just like if I would pee in the cup in front of Joanna, she would be upset.
Right.
So for the same reason, the water pressure goes down. Okay.
Yep.
Okay. Let's see what he says.
Stop.
So the Asian guy says stop. And okay, so Khalili says start. Joanna drops the ball. She should also kick them in the nuts once in a while. I think that'd be very, very productive. Anyway, so Khalili says start. Joanna drops the ball. And when he says start, he starts pouring the water, filling the cup. And then when the Asian guy, Gavin, when the ball reaches the end, he says stop, and then Khalili picks up the water and then measures it. Okay.
A quarter of the ramp was about the same time it took.
How do you know? You didn't take a measurement for the first quarter. How do you know? What is he talking about? Why is he saying nonsense? They didn't measure the first quarter. What is he talking about? This doesn't make any sense.
This is such an awesome measurement, dude.
I
This
know,
is so fucking
How
genius.
could he say something about the first quarter? He didn't measure the first quarter.
To cover the next 3 quarters.
No, she put it down.
How does he know? How
But
does he
didn't
know that the time it took to reach the first quarter is as much as the time it took to reach the next 3 quarters? How does he know that?
didn't they divide the distance, and then she.
No, they took measurement of cups only from the beginning to the end. They never measured 1 quarter. This is nonsense.
Wait, no, she's throwing it down right, like at a lesser distance, right there, right?
You could say no. I could say instead of telling me something about the first quarter, instead of saying the first quarter, you can talk about the last quarter.
Oh yeah.
they measured the last quarter, and since there's no difference between the last quarter and the first quarter, that's what he meant. So
Yeah.
he's wrong. He
It's the
meant the
same
time it
slope.
takes to cover the last quarter. You could say is the same as the time it took to cover 3 quarters. What? That doesn't make. Is this true?
Wait.
That so he's saying what he's saying is the time it took to cover this much is the same as the time it took to cover this much.
Oh, I see. Okay.
That doesn't make any sense.
Wait. So the time it took to cover the last quarter is the time that it.
I don't know. I don't know how he says this. I don't know what he's basing this on. This doesn't make any sense.
Time it took to
So does anybody ask questions? So this he says this at 3:21. Anybody talk about 3:21? Everybody says wonderful and wonderful. Everything is wonderful.
Wait. Okay. So the time it took to cover the first quarter is the same time it took to cover the three or 2 quarters, right? Of the next two.
Somebody finally says flawed experiment. That's good. Or just use a timer. When the angle of elevation of the rank plays a major role in the experiment, yet isn't. Oh, the angle is not mentioned. Really? The angle matters? Galileo proved anti-gravity was a force? What? Stop misleading people. No such thing as gravity. Oh my god. How is it not that the object has moved more weight and density? There goes the gallon of water. Misleading because if we follow what you said, this will lead the ball to speed up to infinity. Oh my god. Mr. Al-Khalili has great cochlear inner hair cells. Why?
But it would speed up to infinity, wouldn't it? If like
You're denying that the ball rolls faster as it declines, or just okay? Look, I don't know. Let's just listen to what he says because this doesn't make any sense. Maybe we should just ask the question. What is it? What are you talking about? 3:21, 3:21, first quarter.
put the double dots in between 3 and 21.
Oh, okay. Thank you.
Mm-hmm.
Okay, first quarter. What is Professor Al-Khalili talking about? He never measured the first quarter. Yeah, I don't know what he's talking about. All right, whatever.
First quarter right there.
What do you mean? That's the last quarter. We don't know anything about the first quarter.
Well, that is the first
You
quarter.
could argue, but he said the first quarter is as much as the last 3 quarters. But he never. Okay, so the first quarter is equal to the last quarter, but the last 3 quarters, we don't know anything about the last 3 quarters. He never measured the last 3 quarters separately. So I don't know what he's
Oh,
talking
I see. Okay, so the time it takes to cross the first quarter is the same time it takes to cross the next 3 quarters if you preserve that acceleration amount from the.
I
the
don't
first
know.
quarter.
He never measured. I don't know. He never measured. So why? I don't know. I honestly don't know. If I knew, I would say I know, but I don't. So I
Right.
want to kill myself. Let me just kill myself. People wonder why I need to kill myself. Now you know. I'm crying so much because Joanna is not here. Joanna needs to be with me right now. Like, how much does she see?
Now we'll see if we're right by placing bells along the ramp. Now we have a
So the first span.
Oh, I see. Okay, so it
This
wouldn't be
is
exponential.
this is 4 meters. This is not 4 meters. This is much. This is like not even 2 meters. So whatever. Okay, let's say this is 1 meter. This is not 4. Where's the 9? What do you mean 1, 4, 9, 16? There's only one span, the second span, and a third span. What do you mean 1, 4, 9? What's going on? So this is 1 meter. This is 4 meters. This is 9. What is he talking about? This is the most confusing science I've ever seen. This is why I hate science.
Let's say from the start, the ball covers a distance
Oh, there's one span. That's 1 meter.
of 1 meter in the first second.
He put the 1 in the wrong place. Who? The editor. Oh my God. The editor is such a dummy dum-dum. This is the 1 meter.
After 2 seconds, it'll have covered.
So after
Well, that
two,
can't be a 1 meter because that's
4.
shorter than 1 meter.
No, but when he says 4, is it 4 from the beginning or this span? Energy? Oh my God, my battery's. Oh my God, my computer is about to die. Okay. Oh my God, saved. So, is this 1 and this is 4? This span is 4, or is this 1 and everything up to this is 4? So I don't know. I don't know.
4 meters. After 3 seconds, 9 meters.
So this is 9 meters. Why 9? It's like, is it? It should be 1/2 AT squared. Whatever A is. So so 1 is 1/2 AT squared, and then after 4, 1/2 AT squared. I don't know what A is. I mean, he's not doing any calculation. He's just telling us like random numbers. Like, where are you getting these numbers from? Jesus.
After 4 seconds, 16 meters. And
Why is it 16? What do you mean? What are you talking about?
so on.
What do you mean and so on? What's the formula?
You recognize this progression.
I recognize this progression? What? 1, 4, 9, 16? Do you
is
recognize 1, 4,
16
9,
meters,
16?
and so on.
What's the
He's,
progression?
he's counting. He's doing time, and then that's distance. So
I would say this is 1 squared, 2 squared, 3 squared, 4 squared. Oh my God. That's the answer? It's really just squares of the integers?
If you recognize this
Oh my God, that's time squared, but it should be 1/2 acceleration times time squared. But 1/2 acceleration is a constant, so it should be proportional to the time squared. So it should always be proportional to, linearly proportional to. So anyway, he found out that when he draws the coordinates, the graph, I don't know if they had graphs in those days, but it should be proportional to the time squared. The integers 1, 2, 3, 4, so it should be 1, 4, 9, 16. Proportional to these numbers.
progression, you'll see that distance goes like the square of time.
the square of time. Okay, yeah. Distance is the square of time.
So why is he showing a rectangle and a circle?
Galileo had found the rate at which gravity speeds up objects. And he'd found another fundamental principle. You can measure the strength of gravity by how much it causes falling objects to accelerate.
Amazing. Oh my God, there's so much to think about and analyze before you can say F equals MA, but they don't teach you that. They just, F equals MA, don't ask questions, F equals MA, well, what do you mean you don't understand? F equals MA, F equals MA. Anyway, the law of falling.
For some reason, my mind just still doesn't get it.
I don't know. We didn't do anything. We're gonna continue.
Okay.
There's part two. Part. Do you know this place? I think it's a famous place.
Italy.
No, I don't think it's Italy. Kalili, I think, is probably in London somewhere. I think this is like a famous promenade in London. I don't know. Like the only time I went to London, I never left the airport.
Is it where Joanna lives?
Maybe. I don't know. Oh. Oh, an apple. Oh, not what we.
When you drop an
We're
object,
looking
if
for measure. Let's see if there's anything else. We need to know more about Galileo. We need more Galileo. Galileo's famous gravity experiment. Let's read this.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber.
I don't care. Galileo's Pisa drop revisited. Okay.
Okay, let's say we go back to Galileo for a second. Galileo's head was on the block, right?
They fall
Anybody?
at the same rate, irrespective
Anybody?
of their mass. Like
Right.
we know what
Federal?
we know what they're
No?
going to do.
Okay. I don't know.
Wow, I'm showing my age. Dave's in the back room going, "Yeah, Indigo Girls." Okay, what did Galileo do? Galileo
Or the
went to
accelerator.
These guys end up banging all their girl students. It's really good to be a professor.
the
Fuck yeah.
top of the Leaning Tower of Pisa, and he dropped
It's like all your girl students, they need to get good grades and you need to give them private lessons. So it's very good.
a massive cannonball and a very light cannonball. Okay. And he showed that those cannonballs hit the ground at the same time. And this was really confusing to people because from Aristotle's time, people thought heavier objects fall faster. Okay. And Galileo said, well, wait a minute, I'm not sure that's really true. Let me test it out. And so he
Even before he tested it, we don't know if he tested it, but you can prove with a thought experiment that this cannot be. Because Galileo said, well, let's think about it. Let's take the heavier one and split it in two.
Right.
And just tie a tiny thread between the two pieces. So it's still going to fall at the same rate. Now let's cut the thread. It's still going to fall at the same rate. That means the two halves each weigh half of the big piece, but they should all fall at the same rate.
Yeah.
So that's a thought experiment that proves that mass should not influence the rate of falling.
Exactly.
did this experiment. And what he
Because it's the
found
force
was
times the mass.
No, it's nothing to do with that. It's just that it's a thought experiment.
Because,
Gravity.
well, no, force times the mass, and then the mass times the mass times the inertia. Well, yeah. So then that would be the actual thing. So you get the force times the mass over the mass times the.
No.
Hold
It's
on.
a thought experiment. Nothing to do with
It's
an
just,
equation.
no, it's just another way to formulate it to think about it. Because so it takes
All
more.
objects. No, Galileo discovered that all objects fall at the same rate regardless of their mass. From
Yes,
a
yes.
thought
Yes. So if
me
you
talk.
have
Let me say it, from a thought experiment. It's just from a thought experiment. No equation, no numbers. Let's go.
the time this one took to hit the ground was exactly the same as the light one. Okay, why is that? Because they're both falling at g. There is certainly a bigger force on this heavier one, but it's also a bigger mass. And so its acceleration is g. On the lighter one, there's a
That's incredible. From the thought experiment, now you can think about the force acting and causing the acceleration,
Mhm.
and therefore Since the acceleration is a constant, but the mass is different, therefore the force must be greater.
Yes.
But it must be proportional to the mass. So the force must be proportional to the
Proportional
mass.
to the mass. Yep. Yep.
The force must be proportional. From this, you can see that the force is proportional to the mass. And if you get it, okay.
Smaller force, but it's a smaller mass, and so its acceleration is g, and so they both hit the ground at the same time. But now let's redo.
That's really a good fitted shirt. It's like a perfect fit. It's not too big, not too small. But he shouldn't be wearing a turtleneck undershirt. That doesn't make any sense. Unless it's like it's winter. Anyway, he shouldn't show his arms. He should have his sleeve all the way to his wrist.
Let's think about how this would work. We already know how this works. We've seen billions of examples of this. Let's focus on how this would work from a quantum like gravity perspective.
No quantum gravity. I just want to understand the history of science.
Galileo's experiment. And
But
we're
we
gonna
already
do
seen this. We already know what this is.
No, I don't know.
2 steps.
This is going to get really complicated really fast. You're not going to follow. I give you 10 seconds and you're gone. You're lost.
Let's drop them sequentially. So we're not going to drop them at the same time. We're going to drop number 1. And we're going to measure T1. And then later on, we're going to do the second experiment. We're going to drop number 2.
Can you guess how it is that he's writing on the board and he's writing normally, but we see it normally? How is that? Shouldn't we see it like in the mirror image? How is it possible that we see it normally if he's writing normally? Because we're looking at it from the opposite direction. Shouldn't we see it like mirror writing?
Oh
Yes.
yeah, I see what you mean.
So how does that work?
It's like
we're going to measure
What's the answer?
T2.
wow, I don't know.
And now let me ask you.
Hold on, let me think about that.
What are you chewing?
A potato chip.
I don't allow that. I don't allow that in class.
Okay.
Anyway,
so,
wait,
my
are you
bad.
fat?
Yeah, I'm fat.
No, you should eat protein. You should eat, instead of potato chips, eat like pig ears. Do you know like pig ears?
Yeah,
Fried.
yeah.
So you should eat those. Those are a little better for you.
Okay.
Or just chew beef jerky.
Okay.
Beef jerky is like protein. It's better for you. Do you go to
So
the
wait,
gym?
No, I don't go to the gym.
Why not?
No,
Why don't you
I stay pretty much like fit, like doing nothing.
Oh, so you're fit or you're fat?
I'm fit.
Okay.
You a question. Is T1 equal to T2? And let's ask the people at home. And I'll set up your polling so you can answer. Is T1 equal to T2? A is yes.
Wait, what do you mean?
B is no.
It's the rate.
C
the time,
is I'm too tired to answer.
I don't get it.
I'm still in my pajamas.
Of
at
course
home.
it's yes. Of course they're the same time.
Why don't you guys discuss it for a
Why
few
should
seconds
it
with your
why would
table?
it be different if you drop them sequentially or drop them at the same time?
And let's come up with an answer.
"10 hours later, 1,000 years later, 10,000 years later."
I was just thinking that. Oh shit.
Everybody's still thinking. They're thinking.
That's
thinking.
probably why he does that.
Everyone is slowly committing suicide, one after the other. Oh my god. Oh, his mic dropped. Where's the sound man? Sound man. Sound man. No? So it's no? Oh.
Well, if they're yelling at me, they should put it in all caps, shouldn't they? Isn't that how you yell on text?
How long ago was this? Is this like a
See, the
thousand?
good
Oh, it's
news
8 years ago. It's
they're
before
paying
the
attention.
invention. It's before the invention
Right.
of the internet.
That's the good news is they're like, hey, we can't hear you, which indicates maybe they want to hear me, that's all right. Okay, so no is the right answer. T1 is not equal to T2, even though it was in this case. This is still true. Nothing wrong with that. So what is going on here? How is it possible
the
T1
distance
could not
is
be
greater
equal to T2?
over there because
Any
they were
thoughts?
What?
They
What
were
is he talking about?
they were dropped at the same location. One of them has a smaller radius, so it's going to take
Turn on
more
your mics.
time for T2 to drop.
I don't
Turn
get
on
it.
all your mics.
Why would it
And
be
let's figure
no?
this one out.
Because
How could this be?
Okay. Possible
T2's
that
got a smaller
both drop at
radius
the
than
same time. Yeah, that would certainly be true. They
T1.
might drop at the same time.
And
Then
so if they're
maybe
dropped
there's
at the
some
same
time
location,
difference. And our clock is real
T1
good. Our stopwatch, we can say this
drop
drops
first. It
there,
would hit the ground
measure
first.
those times. T1 is equal to T2. Okay, what is the planet that we're talking about? Well, let's talk about the one that we're.
Even though they fall at the same rate,
Okay.
they one of them's got a larger radius.
And he goes, well, it's a big ball of gas and it's in outer space. And I go, that's great. You know what? Let me tell you a secret. You're on a planet that's floating around in outer space too. And he's like, what? What are you talking about? Yeah. What's your name? Megan? Okay, good. So let's say they're exactly the same height. Yeah. Our atmospheric conditions. Okay. Let's make the caveat. There is no air in either of those cases. There's a great video on YouTube from David Scott, the astronaut. He went to the moon and he took a hammer and a feather and he dropped them and they hit the ground at the same time. Big old hammer and a feather, and they hit the moon at the same time. Why? There's no air on the moon. They both accelerate at the same rate, and if you get rid of all the air, it really does hit the ground at the same time, which is kind of weird.
So the acceleration.
Okay? Acceleration is basically the same, except you're getting close. Let's think about this right here. What force is acting on the ball? Gravity. But we just said no isolated force exists. I can't just draw one arrow in space and say that's our force. There must be something else. What? I was stretching. Yes. That's equal and opposite force.
Oh, the Earth. Oh, so when they do it differently, so when they drop together, they do because he's taking into account the fact that the Earth is moving up. Equal and opposite.
Oh yeah. I
So
see what you mean.
On the left, the Earth is moving up a little faster.
Oh, I see.
As the ball falls towards the Earth, it is pulling up on the Earth. Is this right? I mean, when I hold this pen up here and I drop it, am I saying that the Earth gets pulled up towards the pen? Yes.
No. The answer is no, because when you held the ball here, you were already tugging on the Earth. By letting go, this tug is not changing. This tug was always there. You didn't change this. So the answer is you. Do you understand?
No, I didn't. I couldn't hear what you said.
Wrong.
No, he's right.
No, he's wrong. The Earth is being tugged before we let go of.
No, nothing
ball.
is being tugged. Everything is being pushed.
No, the Earth is being tugged.
No, nothing is being tugged.
When I let go,
You're being pushed.
No. This ball
The
is
Earth
here.
is being pushed too.
No. This ball is here. And my feet are pressing against the Earth, so the Earth is not being tugged. So I mean, the Earth is being tugged, but I'm pushing. Okay, so maybe he's right. 1 second. So
yeah, he's right.
I'm standing in the way between the Earth and the ball, and then I let go. When I let go, they tug each other and they move towards each other.
Yeah, because the center of mass is going to be for this. That's a
But
smaller mass.
the question
the
is,
center of mass is here. So the Earth is not going to move, as
But the
much
question
here
is-
because that's the lesser mass. So there's more
Question.
push in this case here
I don't
and
know.
here.
Okay, I don't know, and I don't care that much, but I do care a little bit. So when I'm here and I let go, now the Earth is accelerating upwards and the ball is accelerating downwards. Whereas in this case, the ball is accelerating downwards and the Earth upwards, but the Earth is being tugged upwards a little less, and this guy is being tugged downwards. So it's being tugged at the same amount, but the Earth is being tugged a little.
Wait a
So the
second.
question is, two balls of the same mass, do they attract each other faster than two balls of a lesser mass? I guess.
Yes. Yeah.
Yeah, I guess so. All right. Well, it's not important, but he's right.
That is exactly what I'm saying. It doesn't get pulled up very much. Why? The Earth is pretty massive compared to the Pen, right? So why is the time no longer equal? It's because this one we said was big. This one is small. So what happens to the Earth?
There's a problem though. I see a problem with this.
That's exactly right. It moves
So
up there. So when the
this
ball-
object here takes time to communicate force around here to push this object here.
Whatever.
More.
It's not
In this case,
important.
Or
I want to get.
we're-
I want to.
here.
This is.
hold on it with less force.
It's
And
interesting.
this is kind of like weird to think about. And you might suspect that
Plus,
the difference in
the
time is gonna
speed
be
is going to dilate heavily.
Yeah, I
But-
don't care. I don't care about the time dilation.
very small.
Okay.
T1 is certainly less than T2, but it's not much less. And I wanted to figure out how you would do this experiment. So I did a calculation the other day. It turns out if you can measure a difference in time that is 1 femtosecond, and we know
Femto's negative 15. 10 to the negative 15.
what femto is? 10 to the minus 15. Okay, that's a femtosecond, which you can do, right? You can do that with atomic clocks. You can do that with lasers. So a femtosecond difference in time, you could measure. How big an object would you have to drop and from how high? It turns out if you drop a tennis ball from the top of the Empire State Building, and then you drop an oil tanker full of oil from the top of the Empire State Building, and the whole
But
thing,
really,
you will get
this just has the Earth has to like stretch up a little bit.
Yeah.
So,
of about
okay.
femtosecond. So it's a slightly difficult experiment to do, but it really does sort of indicate that everything is pulling on everything else. In fact, the moon in its orbit, right? The Earth is pulling on the moon, but the moon is pulling on the Earth. Where do you see that? In the ocean, the tides. The only reason that we have tides is because of the moon.
Yeah.
The moon going around pulls on the Earth. The surface of the Earth pulls on the ocean.
Okay, that's
Those oceans
not
bounce back and
what
forth
I
between the
wanted to
moon.
know about Galileo. That's not Galileo. That's like nonsense Leo. Let's talk about nonsense Leo. All right, Galileo's inertia.
Galileo played with balls rolling down and then up ramps at
He played with his balls. He let Joanna play with his balls.
various angles.
So you see, he lived in 1564 to 1642,
Uh-huh.
and Newton wrote Principia. I think it was like already 1690. So 50 years after Galileo died, Newton wrote Principia or something.
Found that a ball rolling down a ramp and then up an identical ramp came to the same height. If the upward ramp were less steep, he found the ball wouldn't slow down as quickly, which meant it could travel for a longer time. It would then end up at the same height at which it was released.
Let's listen again.
Oh, okay. That's cool.
Galileo played with balls rolling down and then up ramps at various angles. He found that a ball rolling down a ramp and then up an identical ramp came to the same height. If the upward ramp were less steep, he found the ball wouldn't slow down as quickly, which meant it could travel for a longer time. It would then end up at the same height at which it was released. In all cases, he found that the height of the final position matched that of the initial position, which made him wonder, if the final ramp were flat, in that case, the ball would never lose speed. Or rather, it would maintain its speed, but for how long? Upon thinking about this, Galileo concluded it would maintain its speed indefinitely. In the absence of any retarding forces, the ball has a tendency to move forever without slowing down.
And that
Today, we call this property of an object to resist changes in its motion inertia.
that's why we all end up killing ourselves. Let me kill myself 1 second.
Is that like what kind of poison did you put in there?
Oh, every kind of poison. I
All
love-
of them? Do you think if you just mixed all the poisons together that they would just like neutralize each other due to the law of inertia?
I hope not. It would kill me even more. Let's see Galileo's inertia's track.
Hello, my name's Bruce I'd like to show you my Galileo track. I use it in my class when we're discussing potential and kinetic energy. It's made from one long continuous metal rail, and it forms two different angled ramps together. It allows the ball to roll down one side and up the other. Now, one side is short and steep. The other side is more of a gentle slope. In fact, this side is actually 3 times longer than what this side is. Now, both sides are the same height. So what's this used for? Well, it starts with this metal ball. And the questions I would ask is, what would happen if I were to take the ball and release it from the one side? What would have enough energy?
I would say this is like potential and kinetic energy.
To go up and over on the opposite side. We would have several discussions. I'd have my students make a hypothesis and what they think will happen, and then we'll try it. So let's see. If I release it from this side, will it have enough energy to go up and over on this, off of this end? Not quite. How about if we start on this end? This side is nice and long, gives it a long time for it to accelerate. Will that be enough to get it off of this side? Let's see. It doesn't. And so the next thing is, why not? Well, when we're talking about potential energy, the ball's lifted up to a certain height, and so the idea of energy is that we can't get more out of this than what we put into it. So if I lift it to a certain height, the best we can do is simply
release the ball on one side and then see how far it rolls up on the opposite side. Ideally, we might be able to get it up to the same height, but it shouldn't be able to go higher than the original height that the ball was released from.
So once we see that the ball can't roll off the opposite side, then we start looking at discussion questions such as the change of potential and kinetic energy. Why doesn't it go off the opposite side? Will it continue to roll back and forth forever? And why not? What would
I think this guy's a high school teacher.
He's
Very
smart though.
nice. Yeah.
Smarter than me.
Hi. Nice to meet you. I am Galileo. I am a physicist in Italy. Let me to share my thought experiment to you. Now I put a ball on the top of the curved rail. If I release a ball from a height, what will you predict about the motion of the ball? You can see the ball can reach to the same height at the other end of the rail. Okay. Now, I have modified the shape of the rail. And try the experiment again. What do you think about the motion of the ball right now?
Not critical.
Same thing.
Back to the experiment.
I want to see some equations.
We know he used an inclined plane to roll balls for the purpose
Same
of slowing
thing,
down
more
motion.
angles.
And we know he used a water clock to measure time. Even though this water clock couldn't measure seconds, he did know that the time this clock measured was proportional to the amount of water collected in this collecting device. So if you collected this much water in your first experiment and twice as much water in your second experiment, you knew that the second experiment took twice as long. So how did he do the actual experiment? First, he would roll the ball for 1 unit of time, and a unit here is defined as some specified amount of water. He would let the ball roll and then measure the distance. So maybe after 1 unit of time, the ball had gone from here to here. So how did Galileo do his experiment? Well, he would allow the ball to roll for 1 unit of time, where a unit of time was a specified amount of water, and he would measure the distance. This distance he would call 1 unit of distance, let's say. So if the ball rolled from here to here in 1 unit of time, this became 1 unit of distance. Notice that Galileo wasn't really concerned with whether these units were seconds or minutes or meters or inches. He was looking for proportions, and in proportions, these units always cancel out. So Galileo really didn't care about these things. After he did that for 1 unit of time, he would allow the ball to roll
Square
for 2 units.
the distance over
and then
time.
measure the distance.
Okay.
And again for 3 and 4 and so on. He'd keep doing this for 3 units of time, 4, 5, and so on. And when he was done, he would repeat the entire experiment many, many times, because more data means you can reduce your error. And we'll talk about that now. Here's an example of what Galileo's data may have looked like. So in this version of the experiment, he ran through the experiment 5 times. In the first run through, when he allowed the ball to roll 1 unit of time, he measured a distance of 1 unit. After 2 units of time, he got 4.03, 3, 9.07, and 4, 16.18. Now, he was a good scientist, so of course he repeated this process multiple times, and this is the data he got in each of those following repetitions. Now, with all this wonderful data, now he has to analyze it. How does he take advantage of the fact that he's collected each piece
He has to do the averages.
of data multiple times? Presumably, he wants to find patterns in this data, but how does he use all of it? He's collected it, he should use it all. Well, the answer is he takes the average. And so I'll quickly review what an average is in case you forgot.
I'm a genius. I forgot to tell you, I'm a genius.
You are smart.
Or if you don't know.
Let me take a sip of my poison. 1 second.
To calculate an average, so
Ah.
I want to calculate the average distance rolled in each of these units of time, and I've indicated average distance by a D with a bar over it, and in physics, a bar over a letter generally means the average. What I'm going to do is add up all of my data and divide by the number of data points. So here, I would add up 1.0045, and when I calculate that, look this.
What else can we do? Let's go back.
Let's go back to the
Let's go back. Now this is really confusing. If you want a really confusing lesson about Galileo, here we go.
in the hands of Albert Einstein by Galileo. It was discovered by Galileo. It was discovered by Galileo, refined by Isaac Newton, and in the hands of Albert Einstein, provided a theory of the mechanics of the cosmos. It was one of the deepest mysteries in all of physics. All bodies fall with the same constant acceleration.
In a vacuum, all bodies fall with the same constant acceleration. That's it. That's the law of falling bodies. It doesn't seem like much to get excited about. And yet, just look at what it says. First of all, it says that the effect of gravity on all bodies is the same, regardless of their weight. From Galileo to Isaac Newton, right down to Albert Einstein, that's been one of the central mysteries in all of physics. Furthermore,
This guy's mulatto.
He's what?
He's mulatto. He's mixed. He's half
Oh
white.
yeah, and half Mexican.
No, he's half white and half black.
Oh, got it. Got it.
Or it says that bodies fall with constant acceleration. It's almost impossible even to understand what that means without a marvelous mathematical device called the derivative.
But Galileo didn't have a derivative. He had no idea what a derivative is.
He had a
We'll see today what that means.
a geometric derivative.
I don't think so. I don't know.
And finally, profound and important though all this is, it violates our simplest intuition because it happens only in a vacuum, not in the world we're familiar with.
For all of us, the effect of the Earth's gravity was probably our first encounter with the laws of nature.
That's dangerous for a baby to play with. She could poke her eye out.
Yeah, I was thinking that too.
It's like 1,000 years ago when they used to not care if babies killed themselves.
Right.
7 years ago. They just uploaded 7 years ago. But this is probably recorded like in the 50s or 60s.
Yeah.
Oh, look at this.
Probably the 80s.
1985. This is like before the universe was born.
And whether or not we understand how gravity works. We have
Oh, she broke it. Well, at least that. Wait, on a wooden floor?
And whether or not we understand how gravity works.
That doesn't break on a wooden floor. That's a lie. Stop lying to us. They're gaslighting us.
And whether or not we understand how gravity works.
No, it would not break on a wooden floor. Forget it.
We have an innate fear of what it does. But exactly what is the effect of gravity? Some bodies fall to the earth quickly and directly, while others behave quite differently.
Was that a chick wearing?
We have an innate fear of what it does.
We need to track that.
But exactly what is the effect of gravity?
I don't know. It looks like a girl, right?
Some bodies fall to the earth quickly and directly.
Yeah, that last part.
While others behave quite differently.
I think I
Some
saw a
cases-
camel toe in there.
That's good.
Pull of gravity can be resisted almost indefinitely. To make any sense at all about how and why bodies fall, we need to separate the effect of gravity on a falling body from the opposing effect of the air through which the body is falling. In other words, we have to imagine a body falling, not through the air, but through a vacuum. For instance, what happens if a penny and feather drop simultaneously from the same height? They behave exactly as we'd expect, each falling at a very... In a vacuum, a penny... regardless of their weight. Teen astronaut David Scott
I've got a deal a long time ago. Be a better place to hit the ground to think than is flight.
Mr. Galileo was correct. Nearly 400 years ago, at a time when all the world believed that heavy bodies fall faster than lighter ones, Galileo realized that in a vacuum, all bodies should fall at the same rate.
I think that is Galileo's genius. I don't think anything else he did was as much of a contribution to humanity as this. Like, I don't think his what else did he do? He did the telescope, but he actually just improved it.
Yeah.
And maybe we'll discover that he worked on inertia or momentum. They said. What else did he do? Oh, the Earth-centric, the sun-centric model. I think Kepler. I don't But I think his work on acceleration is the revolution. Inertia. He gave Newton inertia, and he gave Newton momentum.
Galileo couldn't produce a vacuum, but he could imagine one. He pictured a heavy body attached to a lighter one. Would this compound body, he asked, fall faster or slower than the heavy body alone? If the lighter body did fall more slowly, it should slow down the heavy body. So the compound body should fall more slowly.
I actually remember running through this. This gave me deja vu from when I was like really little. I ran through this thought experiment in my mind when I was really young, and I don't know what was my conclusion, but this just gave me deja vu from like really early babyhood.
Slowly than the heavy body alone. But the compound body is actually heavier than the heavy body alone. Therefore, the compound body should fall faster than the heavy body, not slower. Obviously, the long-held view that the heavier a body is, the faster it falls, leads to an inescapable contradiction.
Amazing. It leads to a contradiction. That's so amazing. Wow. So they used to use feathers in order to write. And he's actually probably writing. They didn't have paper. They had parchment, which is basically leather.
Oh, shit.
Yeah, I don't think they had paper yet.
Galileo realized that the only logically acceptable view was that all bodies, regardless of their weight, fall at exactly the same rate once the effect of air resistance is removed. Of course, if all bodies in a vacuum fall at the same rate, the next question is, exactly what is that rate? From common experience, we do know one thing about the rate of a falling body. The speed of a falling body increases as it falls, which means that it accelerates, dropping faster and faster.
No, it's a guy. I think it was a guy.
No, that's a chick.
No, look.
The speed of a falling body increases as it...
That's a guy.
Oh, that's a guy. Fuck.
Yeah, it's a guy.
Why is he wearing a G-string, dude?
falls.
There's something
which means
wrong
that
with
it
this.
accelerates, dropping faster and faster as it falls. Even before Galileo.
He probably died when he hit the water.
I hope so.
Yeah.
Fooling us like that.
A number of scholars tried to formulate a description of this accelerated motion. Some 100 years earlier, Leonardo da Vinci made his own study of falling bodies, driven perhaps by his...
Wow. So Da Vinci was 100 years before Galileo? Did Galileo hear of Da Vinci? Da Vinci means from Vinci. Vinci just means bente, just means 20. He's from 20.
Some 100 years earlier, Leonardo da Vinci made his own study of falling bodies, driven perhaps by his dream of human flight.
How do you spell Da Vinci?
Well, it's D-E, Vinci, V-I-N-C-I, Vinci.
Rather than ask how fast a body was falling, da Vinci asked how far would it fall in successive
Oh, it's Da Vinci, which is the same as Da Vinci.
intervals of time. His theory of accelerated motion was that a body would fall greater distances in later intervals. He theorized.
Look at this. He theorized that in later intervals, a body covers bigger distances.
That those distances would follow the integers. That is, 1 unit of distance in the first time interval, 2 units of distance in the second time interval, and so on. Galileo himself adopted da Vinci's method of description, but he reached a different conclusion on how the distance increased.
So Da Vinci proposed that with every interval, the length covered, the distance covered would just grow linearly. This is a linear growth. This is called a linear progression or a linear series. So in the first period of time, it would cover 1 unit of distance. In the second period of time, which is identical to the first period of time, it would cover 2 units. In the third period, it would cover 3 units. But this would be a constant rate of
distance over time.
Right, but this is this an acceleration? I think it is an acceleration. I mean, it is an acceleration, but it's a linear acceleration. No, something doesn't add up.
No, it's just a constant.
1 and then 2 and then 3.
It's just a
I don't
velocity, right?
I don't know if there's a law of nature. I don't know if there's a law of nature that can give you this proportion.
Speed times distance or something like that.
I don't know. I don't know how you would. Like, I don't know what the velocity is. The distance, if it's 1 and then 2, so wait, altogether it's 3? Oh, wait, this is correct. No, this is normal acceleration. If you say this, he covered 1 here and 3 all the way to here. No, but then 6 all the way to here. That doesn't make any sense because we need it to be proportional to the time squared. Anyway, let's see what Galileo said. So this is Da Vinci's idea. By the way, I can hear myself. So I don't know why I can hear myself.
Oh shoot!
Like, I think
I'm in
I'm echoing off of you.
Yeah,
Yeah,
let me, there we go.
I need to change the name. This is research.
Oh, I
for
see. Okay, so I'm looking at the wrong thing. My
Driving
bad.
F equals MA. Deriving F equals MA.
Instead of increasing as the integers, Galileo's theory was that in successive intervals of time, the distances should follow the odd numbers. Falling 1 unit of
I
distance.
gotta go. I'm losing focus.
Oh, okay, man.
Yep.
Okay.
I'll be back later though.
Okay. I'm gonna end the stream here, and then I'll kill myself, and I'll see you later.
Okay.
All right.
Good
I'll
stuff,
see you
man.
Yeah, I'll see you later, man. Bye.
Yep. Bye bye.
All right. Let's end the stream, and I'll see you later.